Hello, ladies and gentlemen. Welcome back here on the industry stage at Formnext 2023. We are at day 4. And this morning I thought a little bit, should I be sad or not? But I'm not. I'll tell you why. Because until now, this was a great fair. And we have enough highlights to look forward today. For you at the live stream and for you here in the audience, we have prepared a tool called Slido where you can ask questions to us here live on stage. And I will tell you it's worth it. So for you in the audience, you will find a QR code over there. Please scan it with your smartphone. You can send the question to me and you have Slido directly in your stream. So over the last few days at Formnext, we have often heard how important an AM mindset is and that success very much depends on AM-focused design. So we want to take a closer look on that topic today, and I'm really delighted to welcome Dr. Conor Myant, Assistant Professor at the Imperial College of London, on stage to familiarize us with this topic. The title of his keynote is Design for Additive Manufacturing, Current and Future Perspectives. Conor, stage is yours.
Morning. Thanks to everyone for coming, and thank you for this amazing opportunity to talk to you all at this fantastic event. As Sven said, I'm here to talk to you about the concept of what design for additive manufacturing is, try and define that for us, talk about where we are today, what the limitations are with that concept, and where I think it's going to be going or where it needs to go in the future to really unlock this technology. So I want to start off just to remind us about why we're here, as in what are all the amazing things that additive manufacturing does for us. So it provides numerous benefits for engineers, designers, and businesses, from speeding up our prototyping cycles so that we can reach the optimum solution quicker, so we can get through physical iterations of our design and reach that point sooner. Provides greater geometric freedom and design flexibility. It allows us to then employ things like customization of all of our products, so mass customization. It introduces new sustainability opportunities, either through reduced material waste or other knock-on effects like lightweighting. It's provided us with new advanced materials and functionality. We can then also look at creating parts and products from smaller assemblies, less parts, through part consolidation, leads to shorter assemblies, smaller factory floors. It gives us the opportunity to have a truly cost-effective, low-volume production system that allows for the opportunity for at-source, on-demand production, which enables us to look at things like digital inventories as well, rather than physical stocks. And of course, and the thing I think most important, it's a digital process. It's a digital manufacturing system. And because of these benefits, manufacturing industries and nations are adopting additive manufacturing systems to increase productivity, improve export competitiveness, implement supply chain efficiencies and accountability, ensure security and resilience of those supply chains, can be used to address regional economic disparities and create new high-value jobs as well. So you only need to walk around this exhibition to see that this technology space is fast evolving, and it's an exciting arena to be working in, with new innovations and applications arriving all the time. But design is the critical component that translates that technology innovation into real-world, viable, scalable commercial entities. And without design, without developing design processes and methodologies that are specific to those technology innovations, we can't then achieve that commercial success of those applications. So what do we mean by design for additive manufacturing? So traditionally, when we describe design for manufacture, the idea there is that we're applying principles that are primarily concerned with facilitating the manufacturing process to reduce its manufacturing cost. So as early as possible in our development pipeline, We're trying to identify errors. We're trying to identify ways to ensure that we've reduced the manufacturing cost. The later we do that in that development process, the larger the cost is that's associated with making that design change. So it's all about applying those principles and that understanding as early as we can. Design for additive manufacture, on the other hand, is a more holistic process that has concerns across the entire value chain. So we define it as it's the use of design thinking to help identify, validate, and communicate high-value propositions enabled by additive manufacturing. So now, our optimization objective function isn't solely concerned with reducing cost. Cost might be one factor, but it's also about trying to find the optimal part that that technology can produce for you. Now, typically, when we talk about design for additive manufacture, these are the two steps in that sort of process chain that people think of. So we talk about design synthesis. We're looking at how we create our parts in a CAD environment. We're utilizing CAE tools, topology optimization to make exciting lattice structures. And we're concerned with how we can translate those CAD models over to our build platform. So we're looking at things like triangulation, mesh structures, these sorts of things. And then we go into the build stage. So this is where we're actually 3D printing our part. We're talking about slicing, process parameter optimization, selecting the right laser powers and scan speeds, build layout, motion control. But this isn't the only two steps that we need to concern ourselves with. There's a number of important steps before we even get to that design synthesis stage. So there's the data acquisition. This is where we are collecting the information that's going to have a significant impact on the design decisions that we make. So that could be a loading profile across your part. It could be medical imaging, X-rays, 3D scans. Then we need to utilize that data, manipulate that data into the form that we need it to be so that we can make the design decisions. So that could be about cleaning the data, analyzing it, identifying the dimensions that we need. So perhaps we have a full 3D scan, but there's only a few dimensions from that scan that we need. And then, of course, once we finish printing, we're not done. There's still several stages to go yet. So we then enter into post-processing, where we take the part out of the 3D printer. We've got support materials to remove. We've got to finish that part off. Maybe it's post-curing, maybe it's polishing. And very importantly, we've got to inspect the part. We've got to check that we've got good quality control, quality assurance. It's got to pass regulatory standards. And then now we can actually give our part to the consumer. So we've got to have distribution concerns. Perhaps we've got inventory as well, storage, packaging. And something that I think is of growing importance amongst this area is end-of-life considerations. Recyclability, reuse, what happens at the end of these products. And when we talk about design for additive manufacturing, I want us to consider this entire process chain. So for build, when we're making our design decisions, when we're creating that part in our CAD package or in other packages, we need to know the constraints of our build. What is our design space available to us? What does our 3D printer say that we can and cannot do? Post-processing, we've got to think about access to the part. Can I reach those supports to remove them? Can I reach the part that I need to inspect and certify? We need to know what the intent of the part is. How do we intend the consumer to use it, to handle it? How are we going to give it to them? We also have to think backwards about what are the requirements of the data that I need? What's the resolution? What's the data fidelity? And then what's my interest within that data? Do I need to expand it? Do I need to extract specific data points from within that? And then we want to close this loop as well. We should be thinking about customization and co-design processes. We should be bringing in the consumer so it can fully have a part to play in the design of that. And these are all things that additive manufacturing allows us to do, and we need to be building into all of our design thinking. So design for additive manufacturing is or can be one of the most powerful tools at your disposal to improve agility, productivity, and sustainability of your product pipelines. And it should be at the forefront of any investment, training, and business development plan, in my opinion. Without this know-how, without the concepts of design for additive manufacturing and the implementation of it, there's a potential for a knowledge bottleneck, where you lack, or we lack as a community, the design ability to truly untap the benefits of additive manufacturing adoption and digitalization, which will significantly stifle the manufacturing productivity, competitiveness, and innovation opportunities. But with it, you can truly implement a digital manufacturing system across your entire process chain. You can establish and maintain seamless digital threads where each step is driven, automated, determined, and checked by data. And I think that's the kind of process chains, product pipelines that we should be aiming to do within additive manufacturing. So I'm going to give you an example from a research project that we did on respirator masks for hospital workers. So the respirator mask works, its performance is very much down to how well it fits each individual. And it's how you get that seal between the mask and the face. So we were taking 3D scans of the individual, and they could then submit that scan via a web page or some sort of cloud platform. And that's where our digital thread starts. The data is then cleaned, manipulated. We extract that topological information that we want, the dimensions that we want, that we're going to drive the parametric design model. So now we're moving into a CAD package. We're using API scripts to automate that generation of the CAD file. At this stage, we can then perform digital fit tests. Does that CAD model fit the 3D scan of that individual? Does it meet the thresholds that are required? If not, we can go back a stage, we can manipulate the data further, and we can repeat until those thresholds are met. Once we've achieved that, we can then send the part to be 3D printed, where we can implement on-the-fly monitoring, we can update the G-code as we need to ensure that we've got high quality control, quality assurance standards. Once the build's complete, we move on to post-processing, curing the part, inspections, sterilization of the component before it can be packaged up and delivered to the consumer. And we were looking at ways to embed all of that information onto the part itself. So we're embedding barcodes such that that part is traceable and accountable. We know its history, we know where it's come from, when it was manufactured, and it can be sent to the right individual. And it's these kind of product pipelines that additive manufacturing, and I would say more than any other manufacturing process available, that truly allows you to make these types of digital pipelines. And there are, of course, some weaknesses that we as a community still need to address, and that's where we move between each of these steps. And I think particularly between the design, synthesis, and build, or the build and the post-processing, that's still very much a manual handling process. But we should be at a point very soon where this entire process can be completely automated. But the last manual step is the submission of the data, or the collection of that data, and then when the consumer actually receives the part. Everything between there can be completely automated. So how do we achieve this digital future? So we need to connect the fields of design, engineering, and manufacturing to drive this transformation of innovation at the intersection of disciplines to realize the significant benefits that manufacturing digitalization can offer. We need multiple disciplines to come together. We need academia and industry to come together to look at, collaborate, and try to find the solutions to the challenges that we face today, but also the challenges we know we're going to face in the future. So we need to create the structures to act as conduits between academic research, policymakers, civic partners, and industrial stakeholders to ensure high-value, measurable impact. From the translation of research, so we don't just get stuck in our R&D labs or in university labs, but we can then translate that research and embed it into industry practice and make it a commercial reality. We need to train future graduates, university graduates, and we need to train our current workforce, our current users, with the appropriate skills and implement novel design thinking practices. From context analysis, so what is the product that we're trying to do? What is the problem that we're trying to solve? Who is the product for? Identify those problems, ideate around them, prototype, coming up with solutions. That's where the creativity comes in, and then proper evaluation, validation of our ideas as well. So testing, how do we prove that we've got the right solution? We need to train the same people in emerging technologies such as operational technology infrastructure, artificial intelligence, machine learning-driven technologies, cloud-based software platforms, project lifecycle management systems, execution systems, business intelligence solutions, and centralized data management. These are core technologies that I believe that any future designer or engineer needs to be aware of. They need to have coverage across these. They also need to be trained in advanced digital design techniques, such as coding or programming, AI and machine learning, big data analysis, visualization. How do we communicate all of this information back to the consumer, back to our colleagues? Automation and optimization, and I mean that in terms of the design processes, and systems analysis as well. We need to update the current design tools and workflows. These have been developed to represent homogeneous objects, solid, continuous objects, suitable for traditional manufacturing technologies. So our CAD software, our design processes, and our typical ways of going around designing products has been born out of a CNC type way of thinking, out of traditional manufacturing, where we can't, as we build our part, we can't really influence what's going on inside that part. It's just solid. What additive manufacturing allows us to do is to now create that internal structure as well. And we need to then take design approaches, have design tools, ways of communicating and visualizing our designs that allow us to look at that internal structure as well. So the example I've got here is a human femoral bone that's been recreated from a CT scan. It's the image on the left. And then this is now a solid model recreated in a CAD package. And as you can see, as we split through that, we just have this homogeneous, solid data. If we mesh that, a surface mesh, an STL file, we now only have that surface information. But in reality, when we look at the internal structure of bone, it's anything but homogeneous. Now we have the opportunity to really try and recreate. We can look at this sort of biomimicry opportunities to create that advanced material, this type of functionality. Additive manufacturing allows us to do that. Today, we can create these structures. The issue is our design processes and design tools holding us back. The CT scan, so this is another example that I'm providing from our research, where we take a CT scan, this time of a knee joint, as we were looking at knee implants. Within that CT scan, it holds all the information that we need. So not only were we looking at that CT scan, recreating the external geometry of the bone so that we could get the right fit of the knee implant, but we were also looking at the bone density and bone structure inside the patient's bone. And then we were using that to update the lattice structure, the infill structure that we were applying to that knee implant, and we were varying the thickness of our lattice structure throughout so that we could match the density, the mechanical properties and density of our knee implant to the patient's knee. And there's numerous medical advantages for doing that. Okay. An example sort of artifact here. This is a challenge that I give to my undergraduate students on our design engineering course. This is an audio file that has been wrapped in a spiral onto a sphere. It's just a delightful artifact. But I pose this object to the students and I say, how would you recreate this in a CAD package? Drawing that would take days, weeks, probably months to get that as an accurate representation of that audio file. So trying to create objects like this through traditional design processes are just not practical. So what we do is we show the students how to create that through programming, through code. So this is 150 lines, something like that. Could probably do it in far less. It's just code, but we're showing the students that coding is now one of the most important tools to a designer. And I think if you ask our graduates what important skills that they've learned through the 4-year program, I think that most of them would say that coding is the #1 skill that they've walked away from. So we started out as this. This is what we traditionally would think of designers, design engineers. This is where we are today with our CAD environments. Perhaps this is where we're heading, coding or some synthesis between the two. And with that, happy to take any questions.
Awesome. First of all, Connor, thank you so much from my side. Excellent presentation. When I first saw your slide, I was a little bit worried whether I could follow or not. This was an excellent presentation and a very straightforward red line throughout the slides.
Thank you.
So if you have any questions from the audience, you can place them into Slido. Otherwise, I will have 1 or 2 questions if you allow me, Connor.
Of course.
So my first question, we talked a lot about design for AM in the last couple of days, and you look on it from a research perspective. If you look at the industry around, how would you evaluate the maturity level of design for AM, considering what you said, we have to follow the whole process? Mm-hmm. Where do we stand today? What still has to be done?
Great question. I think there's definitely how we apply a lot of our research in my research group is we take the approach that additive manufacturing, 3D printers, can do so much more than we currently ask them to do. And typically, I think what's holding people back is either our own creativity or understanding of the technology, and then the design tools that enable us to do it. So we're having to look for like hacks and cheats. So we look at how we can update the part, perhaps just in the G code itself. And I think as an industry, as we sort of walk around, I think there are companies now starting to enable these things, but it's still quite siloed.
Yeah.
And we need to start finding ways that all of these systems, all of these points along your product pipeline that can seamlessly integrate with each other. And I think that's still a weakness that we have as a community.
Furthermore, you mentioned one thing which was threatening me a lot, to be honest, because you were talking about the things we need to know about in the future. And considering, I mean, let's face it, we have AI. Mm-hmm. Progressing heavily, and I tell you what, it's although I'm really technical oriented, it's super heavy to keep up the speed. Yeah. Then you said you have to think in design of 4 AM. Then your final slide was about the coding experience. Yeah. I mean, we were talking about lack of skilled workforce, and now we are talking about increase the knowledge of these people by 100%.
Yeah,
that is a big challenge.
It's a big challenge. It's a big challenge, and you know, as an educator, that is the challenge that is on me and my colleagues within.
And how do you cope with that? I mean,
Well, exactly. We have to stay relevant, right? And
Yeah.
we've got to stay on top of these technologies and new ideas. And hopefully the idea is that we are the ones that are pushing the forefront of that technology and that development. I think we are entering a transition phase where graduates are leaving with a different set of skills, and we are moving into a digital age, as it were, and to coin a sort of buzzword, but it is true. As educators, we're moving away from more traditional sort of hands-on fabrication and learning in that way, and it's becoming more digitized. And what we need is that digital thread to be seamless, so that students don't have to spend a lot of their time learning multiple different platforms, multiple different coding languages, but can then get on and actually implement these things and practice it, creating new innovations and new products, and see how far they can take it.
Great. Connor, thank you so much. We were running out of time. Sorry for that. What a great presentation. Thanks for being here, our guest on stage. Big applause again for Connor Mayen. Thank you so much, Connor. I tell you what, there are a lot more highlights to come, but before that, we look currently at the highlights here at the Formnext, so please enjoy a few minutes of highlights from the Formnext so that you don't miss a thing, and please stay tuned. In a few minutes, we keep on going here on stage. See you there.